Okay, let's talk about expectation, probability expectation. The easy way and the way I did it in my course, I just defined here's what the expectation operator is. You have a function of your random variable. The expectation is just this integral over the entire extent of your random variable, x, of that function of x times your PDF of x. And you can see a fallout of that is if your function is just x itself, the expectation of x is this thing. It's x times the PDF of x, and then integrate that over all x. Actually, it's more properly defined this way. We define the expectation of x this way, and from there you can derive this guy. But that derivation is not trivial at all. I think it took a couple of 3 pages in the book I looked at. Here are the corresponding discrete expectations when your PDF, or instead of PDF, you have discrete probabilities. Convince yourself that it is a linear operator, meaning the expectation of a linear combination is the same linear combination of the expectations. See that the expected value of a constant, here A is a constant, not really a random variable. It would mean this, you can pull the A out of it, and what's left is PDF itself. When you integrate that over all x, that's just 1. So the expected value of a constant is just that constant. That's good. Moments are sort of special functions, where the function is x to the power k, where k is a non-negative integer. The 0th moment, that would just be 1 up here. You're integrating the PDF, you should get 1. That's y. The first moment, this guy is also called the mean or the average. Sometimes the notation, the expected value of something, we use the overhead bar. And a lot of times for the mean, we just say mu sub x. Sometimes it's the letter m sub x. The second moment, or the mean square, is this expected value of x squared. There would be one way to notate that. This is all it means. The square root of this guy, is sometimes called the root mean square. So the mean square is this thing. Root mean square is you take the square root. Central moments. There, it's kind of like the moments, but we subtract off the mean. That will kind of center it. And it just means this. Again, the 0th central moment, this would all be 1, and you're just integrating the PDF, which would be 1. The first central moment, this k is 1. Well, then you've got x, f of x, which is the expected value of x, and you subtract off mu of x times 1, basically, because you're going to be integrating the PDF again. You're just getting the mean minus the mean, which is going to be 0. So that's that y. This second central moment is called the variance. The square root of that guy is called the standard deviation. This is all pretty basic stuff. So the variance of x, you can use this notation. What it means is this. It also means this. You could multiply this out, and you'd have this. Then because it's a linear operator, this expectation of this whole thing is the expectation of the individual pieces. And these mu's are constants now. They're not random variables, so they can be pulled out. And you're left with this. The variance is that second moment minus the square of the mean. Or you could also say that second moment is the variance plus the square of the mean. So that's all the definitions of those guys. I'm going to do an example, but first let's do a quick review of even and odd functions. Even means the left side is the mirror image of the right side. Odd means it's like the opposite. It's the mirror image flipped upside down. And a function could be neither. It doesn't have to be either even or odd. But here's where it helps. If you're integrating an odd function over a symmetric interval, you just get zero. Because, the left side wipes out the right side. And if it's even, instead of integrating over minus a to a, again, over a symmetric interval, you can just integrate from 0 to a and double it, which makes whatever's on the right side, the left side would just double it. So that's a trick when we take some of these integrals, because taking these moments and stuff is a lot of just taking integrals. So let's do this guy. Find all these things. Mean squared, and the variance. This guy with this PDF. Well, the mean, you just put in x times the PDF, which is this guy, and it's only from -1 to 1. Oh, I can pull out the 1/2. I get x squared plus x. X itself is an odd function. X to some power is odd if the power is odd and even if the power is even. So the odd guy is going to be 0. And the even guy, we can integrate, instead of from -1 to 1, from 0 to 1, double it, so cancel that half. So here's the only integral you'd need to take. That's pretty easy. That's a third. For the mean square, got an x squared up here times the PDF. Pull out the half again. Here's what it is. And again, we have an even and an odd, and the odd part will go away. So this is x squared again. It's another 1/3. So what is the variance? It's that mean square, 1/3, minus this mean squared. So it's 1/3 minus a ninth, 2/9. One more quick example. Here's the PDF. Confirm it's a legitimate PDF. What that means is the integrand better be greater than or equal to 0 everywhere, and it's got to integrate to 1, and then find the mean. So 1 over x squared is certainly greater than 0 for all x greater than 1. It approaches 0 as x approaches infinity, but it's always greater than 0. So that part's good. What does it integrate to? Let's integrate this guy from 1 to infinity, because that's where the x's are valid. Well, let's see. X to the -2, raise it, it's x to the -1. It's minus, so it's this guy. It's in the limit of this as x goes to infinity, which is going to be 0, plus when I put in x equals 1, I just get 1. It'll be minus a minus. So anyway, it does integrate to 1. And what about the mean? There, I multiply PDF by x. I get 1 over x. That integrates to natural log. Limits are 1 to infinity. And upper limit is infinite. This is kind of weird. You get a mean of infinity or the mean is undefined. This is a possibility. You didn't do anything wrong. We will rarely encounter such a thing, but it is possible to be a legitimate PDF and have an undefined mean. I'll do some more examples in a later video.